Hello, everyone. Welcome to this presentation. So in this project, the topic is called Exploring Quantum Bootstrap Sampling for AQP Error Assessment. This work is finished by collaboration with my student, Raya Jahan, as my co-author. So here today, we have Raya to talk about this research for you.
Hello, everyone. This is Rajahan. Today, in this presentation, I'll be talking about our research paper that I have co-authored with Dr. Feng George Yu for the paper called Exploring Quantum Bootstrap Sampling for AQP Assessment. And we're grateful to the organizer of DEXA conference for accepting our paper. Um, and yeah, I'll talk about our research paper in this presentation. So um, this research paper, in this research paper, we have introduced how to do the error assessment, how to assess the error assessment in approximate query processing, in short, AQP. So in the era of big data, computing complex queries requires a tremendous amount of time, and it imposes emerging challenges in many computing fields. And approximate query processing, in short, AQP, it aims to reduce this original big data into small data by employing several sampling methods and statistical estimators to provide quick and accurate approximated query answers. And in this field, bootstrap sampling is a non-parametric statistical method that can produce estimations of the error for a given AQP answer, even when the statistics of the original data set are unknown. And however, this bootstrap sampling, it requires producing a large number of bootstrap resamples, which are random samples with replacement. And the larger the number of bootstrap samples generated, the better would be the accuracy of the error assessment. But this procedure is computationally intensive, and when we require a large number of bootstrap samples. And different from classical computers, which use classical bits, quantum computers are developed to compute based on qubits or quantum bits. And this qubit can be both 0 and 1 at the same time, following the phenomenon of superposition. And in this paper, we have introduced quantum bootstrap sampling framework, in short QBS, to generate bootstrap samples on a quantum computer and produce an error assessment for AQP query estimations. So the objectives of our research paper is to design a QBS framework for AQP error assessment that uses the Hadamard gates, which follows the phenomena of superposition, then quantum random access memory, then quantum counters to count the number of ones from the tuple results, and a ripple carry adder to do the sum and average aggregation, to implement the sum and average aggregation functions. And we wanted to leverage quantum computing to generate bootstrap resamples more efficiently. And we have implemented quantum circuits that can replicate classical bootstrap sampling tasks. So what is bootstrap sampling? Suppose given there is a sample y is equals to starts from y1 till yn. It has an array from an unknown distribution f. But if we want to sample it out in smaller proportion from this original big sample, then a bootstrap sample, if we denote it as y star, then we can keep it in an array of y1 star to yn star, and it can be obtained by randomly sampling n times with replacement from the original sample y. For example, if n is equals to 5, then we might obtain various bootstrap samples with different combinations, such as y1. Y1 can have y5, y3, and y1 and y2 and y1 at the same time. It can have multiple different combinations of bootstrap samples under one bootstrap sample. And if we want to, after summarizing the frequency of each element sampled, we can obtain the frequency distribution of a bootstrap sample, and we can keep it in the frequency hat is equals to f1 hat from starting from f1 hat till fn hat, where the fk hat can be written as the summation of y I star. If it's similar or not, we will check it to the bootstrap sample. Then we can sum it up, and we can divide it by the total number of samples, which we have denoted as 5. Here on the right-hand side, we can see the figure 1. It depicts the examples of bootstrap samples and bootstrap distribution. And here the angle theta can be denoted as the statistical function, which is the mapping or operator of the frequency distribution. And usually we do not have all the information of the frequency distribution f, but we can only calculate an estimation of theta from the given sample y, which can be denoted by theta. And for each bootstrap y star, we can generate a bootstrap replication of theta hat. So our research problem focused on the query execution and how we can assess the error assessment of those query estimations. Suppose there is a query select aggregation function of some attributes or of any attribute from a specific table where there is a condition attached. And there are two problems that can be addressed. The first problem is it is a high computational cost of classical bootstrap sampling. And there is also a lack of efficient quantum-enabled frameworks for AQP error assessment. So there are thousands of studies that has been done in the past regarding the classical bootstrap sampling, but there is a lack of efficient quantum-enabled frameworks for specifically AQP error assessment. So our goal in this research paper is can we design the quantum bootstrap sampling framework effectively to leverage and reduce the time complexity of bootstrap-based error assessment in AQP? That should be our goal for this research paper, and we have addressed this research problem in our research paper. So if I go back in earlier 1994, then their authors, Efron and Tape Shirani, they have introduced in 1994 bootstrap sampling for statistical error estimation, which was widely adopted in AQP. In the year 2022, you and others, they have used optimized Bootstrap for AQP, but they have completely relied on classical computation, which is resource intensive. And Lee and others, Lee in the year of 2019 and Liu in the year of 2009, they have also outlined foundational AQP frameworks using sampling and random walks. But the emergence of quantum computing for AQP has risen from the year 2024, where Wu and others, they have produced a hybrid classical quantum amplifier using Grover's operator and quantum random access memory for rare group detection in AQP, but their focus was on selectivity issues and rare event amplification. It was not focused on bootstrap sampling. And then in the year 2023, Fallock and others, they have compared QRAM architectures. For example, bucket brigade QRAM, fan out QRAM, flip flop, EQ, EQ GAN, and then PQC QRAM architectures, showing the advantage of QRAM in speed and scalability over classical random access memory. And in the year 2024, Jiang and others, they have developed a simplified quantum counter that can act as an accumulator for summing the binary outcomes like 0 and 1 based on Grover's algorithm to reduce the gate complexity in NP-hard problems. So there has been a lot of studies in the past, but none has addressed the error assessment of AQP. And they have explored quantum sampling and memory access, but they have not applied quantum methods to accelerate bootstrap-based error estimation in approximate query processing. So in our paper, the research methodology is designing a hybrid quantum classical framework to accelerate bootstrap-based error estimation for AQP. And it comprises of two main quantum modules. The first one is quantum resampler, and the other one is quantum counter. So what is quantum resampler? First, this is our architecture. This is the quantum circuit that we have designed. And it shows that how can we employ the quantum superpositions in order to generate random sample IDs with replacement if there is already given a set of tuple sample results. And how does this superposition, how does this phenomenon of superposition generate random samples? First, the n-qubit superposition bit string, it converted to decimal, it will represent the random numbers for resampled tuple IDs with the same probability. And in addition, the quantum superpositions, it will not inhibit repetitions of random index numbers. It is observed in different quantum measurements that the same index number generated from the superpositions, it can be repeated. And this enables us to sample with replacement of the tuples in the given sample data set. Therefore, the quantum superposition, it can generate uniform random samples with replacement from the given sample data, which can be used for bootstrap sampling. And with the bootstrap sample index number I generated, we can employ quantum random access memory after sampling the IDs randomly. We can employ the quantum random access memory to convert those indices I to the tuple sample results yi. Then after quantum resampler, we have introduced quantum counter, in short QC, to sum the tuple result values in quantum bootstrap sample. We employ this quantum counter, which can be denoted by QC, and it can perform counting on qubit inputs. And the quantum counter, it will count the sum of the corresponding value of I in a quantum bootstrap sample, which is encoded in the ket of yji, and it can be either 0 or 1. And the quantum counter, it comprises control registers and counter registers. Each time there is qubit of one ket input to the control registers, the counter registers will increment by 1. And this represents a binary counting number in LSB format, which is the least significant binary format. And the complete circuit would integrate multiple parallel quantum resampler modules, which can be feeding into a QC. And the final count is measured and scaled on a classical computer for our research paper. So here we can see the quantum resampler circuit. How does it look like? This figure, it depicts the circuit design of the first step of our framework, which is the quantum sampling framework, and it is the quantum resampler. So firstly, we have initialized the input states as 0, and then it goes through the Hadamard gates to simulate the randomly sampled indices with replacement, and after that, we have employed QRAM to translate the random sampling indices to the sample tuple results. Then we have quantum counter. This is a simplified quantum counter circuit to count the number of qubits in one ket state from the output of a quantum resampler. And these control qubits, it can be either 0 or 1 state. And these counter qubits, these are initialized as 0 state. And it accumulates, this quantum counter, it accumulates how many control qubits are in the state 1. And the output number, it represents the total of tuple results of 1, which means that it's selected in the count query, which then can be used to compute the Bootstrap replication. And these counter qubits are connected to each control qubit using Toffoli and control NOT gates. So here in this figure, we can see the architecture of simplified quantum counter, and we can see the Toffoli and the control NOT gates in the diagram. Then we have merged the quantum resampler and quantum counter in one circuit to do the quantum bootstrap replication in our research paper and to implement the quantum bootstrap replication. And it illustrates the overall quantum bootstrap sampling framework. Here, the sample tuple results from the multiple QSA in parallel will be fed into the quantum counter QC. And this quantum counter will count the total of non-zero tuple results in each bootstrap resample. And it can be measured and converted to a classical bit value in LSB format to produce a bootstrap replication. So here in the next slide, we can see the quantum random access memory implementation, and it leverages the insights from the bucket brigade scheme. And we have initialized our experiment with 3 qubits in the 0 ket state. And in this circuit, each 0 ket, it goes through the Hadamard gate, resulting in the superposition that generates all possible paths simultaneously, and it represents 2 to the power cube, which is 8 possible memory locations. And the superposition, it undergoes a QRAM, which encodes in a quantum memory address, and it retrieves the data set from those memory address. And for the demonstration, the QRAM in this experiment is initialized using a static array where we have introduced each odd address to be having the value of 1, and each even address has a value of 0. And in the AQP application for a count query, Value 0 means the tuple result is 0 or not selected, and 1 means the tuple result is 1 or selected. And the values of both 0 and 1, it will be encoded as 0 and 1 respectively, 0 ket and 1 ket respectively. And we have employed Toffoli gates, also known as multi-control NOT gate or MCX gate, to flip the data qubit according to the states of the address qubits. Here, X0 gates, these are employed to control the address qubits to match the bit string pattern in the data array for the quantum random access memory. In the next slide, we can see the quantum counter representation. This is a simplified quantum counter to count the number of qubits which are in one ket state from the output of the quantum resampler. And here the output number, it represents the total of tuple results of 1. That means it's selected. And it can be used to compute the Bootstrap replication. And the number of control qubits here, we can see we have initialized as 8 control qubits, and the number of counter qubits is 4. And the function of the quantum counter is to count the total of 1 states in the control qubits, and the control qubits are also initialized as 0. And it undergoes the Hadamard gates to generate a superposition to simulate all possible states of the control qubits. Initially, all the counter qubits are initialized as 0, and the counter qubits are connected to each control qubit using, we can see here, Toffoli and control NOT gates. And to simulate the quantum counter for each quantum bootstrap sample, we run the quantum counter circuit using the AR simulator with 1 shot each time. So for the data collection and analysis, we have conducted 1 to 4 bootstrap replications using IBM Qiskit libraries with 3 qubits representing total of 8 sample tuples. And for sample encoding, we have initialized a static array for quantum random access memory input, where odd memory addresses are assigned a value of 1 and even addresses are assigned 0. And the quantum resampler QSA, in short, it generated uniform random sample indices with replacement via Hadamard gates and QRAM. And the quantum counter, QC in short, computed the count of selected tuples, which has a value of 1 by summing up the qubit states from the resample data, implementing multi-controlled gates. And we have used Qiskit's AR simulator for circuit execution and measurement. And we have reversed the bit order to align with human readable outputs. So for the results, we have obtained the uniform sampling with replacement, and it has been achieved via quantum superposition of address qubits, which has been passed through QRAM. Then we have tuple counting. The quantum counter, it accurately computes the number of ones in the resampled tuples, and it has represented the selected rows. Then we have immediate bootstrap replication. In each measurement, like each measurement of the bootstrap sampling that we have done, it directly yields a bootstrap replication without any further post-processing. So in table 1, we can see all the possible QRAM inputs and outputs. Each row, it correlates to a possible state from sampling measurement results. And when the address is odd, the data qubit returns 1, which is consistent with our encoding mechanism. And in the second table, we can see it depicts an example of quantum counter output during one simulation. Here, the input control qubits are like the ket of 5 ones like 0, 0, 0, and 5 ones. Namely, the control qubits 0 to 4 are in the 1 ket state. The output of the quantum counter or the counter qubits is 0, 1, 0, 1, which can be denoted as decimal of 5. Therefore, we can say that the quantum counter, it correctly encoded the total of ket ones in the control qubits into the counter qubits. So here in this figure 4, we can see a distribution of QRAM output states where it depicts the frequency of each quantum state being sampled. And after 1 or 2 4 experiment shots, the data qubit value having 1, which are the odd addresses, they have similar frequencies to even addresses. And it verifies that the functionalities of superposition are intact in our experiment. So for sum and average queries, to process the sum and average queries, we this is our future work, and we will implement the actual numeric values instead of binary values, 0 or 1, and it can be employed for input sample. For example, we can keep it in the input sample of s equals to u1, u2 till un. We can keep it in an array, and these values will be encoded in QRAM using a fixed width binary format, for example, using 5 qubits, values up to 31. And the QRAM, it can map an address state I ket to data value yi ket using Toffoli and X gates. And to accumulate the QRAM outputs, we can employ the quantum ripple carry adder circuit that can add the QRAM outputs to an accumulated sum variable. And then for calculating the average of the samples, we can divide the sum, the direct total values of sum over the number of samples that we initialize for our experiment. So if we want to discuss about our research paper, the practical and theoretical implications would be it's efficient because quantum bootstrap replication, it is executed in constant time, order of 1 per sample due to quantum parallelism. And it is also scalable because the proposed quantum framework, it supports parallel generation of bootstrap samples via multiple QSS circuits. Then, but there are some limitations. In our research paper, there are some limitations of hardware constraints. And the current noisy intermediate scale quantum devices, they support limited qubits. So it's one of the limitations. And our research, it simulates the count aggregation only. And encoding data for sum and average, it is our future work. And the experiments are based on simulated tuple values, the real world data sets. We have to integrate it into our research paper for further experiments and research. So our future work would be to extend to sum and average aggregation functions, to leverage the quantum ripple carry adder circuits and multi-bit QRAM data encoding for numeric tuple values. And we will test it on real-world data sets. We will integrate the real data to evaluate the system under realistic database workloads. And we will scale it to hardware implementation as well. We'll transition from simulation to execution on real quantum processors as they evolve. So to conclude this research, I would say that we have proposed a novel quantum bootstrap sampling, in short, QBS framework, combining quantum resampling and counting for error estimation in a QP task. And we have implemented quantum circuits using IBM Qiskit to replicate classical bootstrap sampling via quantum methods. And we have verified through multiple measurements and tests that the system reproduces expected sampling behavior and count accuracy. So if any of you have any question, you guys can reach out to us through email. Here I have provided the emails of my professor, Dr. Feng George Yu, and also myself. If you have any question, you can reach out to us. Thank you so much. Yes, that would be it.
Thank you. Just one addition is if you want to look at the source code in this paper, it is included in our paper published. So, and if you have more questions, please feel free to email us. Thank you so much.